Hello, guys. How are you?
Hello.
Hey,
Hey, welcome. Daniel, Aburva. Uh, I think I can get started. Uh, did you guys finish module 2?
hey guys, I just finished my homework today, so I didn't.
Okay. Assignment 2?
Sorry, no. Homework one today, assignment one. So I didn't read anything this time, Rufy.
Okay. Okay. That's fine. That's fine. Even like I was off last week, so I was like over ambitious. I said I'll kind of finish assignment 2 and week 2, everything, but didn't happen. So
Yeah.
I started going through week 2, and what I can do is I can share my notes and then we can discuss as we did last time, and like chime in whenever, like if you have anything to add.
All
Uh,
good.
so let me share my screen. I don't know which screen it is sharing. Okay, so I want to share a different screen. Do you change? I have 3 monitors, so it's like it's sharing. Share. Okay. Desktop. Okay.
Did anybody do the videos for this week? All of them, I mean.
Not I did like there are like 2.3 like 3 sections. So I just finished one and the quizzes.
Oh.
Yeah, I finished them.
Oh, you finished them all, Malcolm?
Yeah,
You are awesome.
it's just the month is going to be busy, so I'm trying to get ahead as much as possible.
So can you guys see my screen?
Yeah,
The multi-class classification, that's the one that's showing, right?
yeah.
Okay. Yeah. So think let me bring up Zoom windows. Okay. All right. So chime in like if anything anybody wants to say or add. I will just go and start walking through. So this week we are going to study multi-class classification. And I think overall this week's, I think I just took some notes. Module 2. So like we have these, like multi-class classification, perceptron, multi-class examples, and fairness in classification. I just left here. So I finished all these 3 videos. And these are the what do you call the the PDF headings. And so
So homework is from week 2, week 3. Like which week are we in right now? Week
we are
2?
in week 2, but homework assignment 2 is going to be week 2 and week 3. And assignment 2 is due, I think, September 24th. So we have some time. I think we have like maybe 2 weeks.
2 weeks and 2 days.
Yeah.
2 weeks and
So
2 days. So it's pretty much throughout the course is going to be you read in parallel, you do your homework. So it's
yeah,
together. Okay.
yeah, yeah. Usually what I do is I finish the videos, I read the assignment, then I finish the videos, and then I jump into the assignment.
Mm.
So I think the assignment, I do have the assignment also. I think, assignment. So this week's assignment is gonna be feed forward networks. Okay, I don't have the assignment downloaded somewhere. Okay, I can just go to the website. Okay, assignment 2. So there are 3 or 4 questions. Question 1 is around optimization. Part 2 is deep averaging networks. And question 2, question 3. So 3 questions. So that's the assignment.
Mm,
And we have to use PyTorch this time.
okay, yeah.
So it's based on feed forward networks, word embedding, and generalization. So that's the assignment. Okay, I will jump to my slides. So anybody has taken a stab at the assignments, or can we just jump into the lecture?
Yeah, then let's go lecture. I mean, unless
Okay.
anyone else has ideas and notes.
Yeah. So I'll just start.
Yeah.
So last week we studied binary classification. We studied binary perceptron and linear regression. So it was like simple. So this week his focus is gonna be on multi-class classification, where you have we have n classifiers. So that's why it's multi-classifier. So if you have this data like 1, 1, 2, 2, you could classify. There's a separate classifier for each one of these datas. Uh,
I thought a separate class for each of them. And you mentioned like, yes, having a separate classifier for each would be one way of doing it, but that's not necessarily what we're doing, right?
Right. I think that's what I picked up. And then I think then he enters into these 2 techniques, uh, like different weights. So you're saying there are no 3, like there are no classifiers?
I'm just saying it's not necessarily n classifiers for n classes, right?
Yeah, I think for the so you described the 2 methods, the different features versus different weights. So for the different features, I think it's basically different weights, it's basically the n classifiers, because each classifier will have its own dimension in the weight vector. But I
Yeah.
remember, yeah. Mhm.
And different features, I think. So he said like there is 1 vector per class, and that's different weights. That's why DW. It's used with neural networks. Then there is another technique. It's called different features per class, and it's used for structured classification.
What
And
does structured classification mean?
so I'll cover it. I think
Okay.
I took some notes. So like different weights, what you're trying to do is you're fixing, this is fixed. So the idea is similar to 1 versus all. That's what he says. We have fixed set of features, try different weight vectors and identify the highest dot product, and that becomes your prediction. So you have different weights, and you fix the features, and that's that. And DF is you have fixed weight vector, but you have different features for a hypothesized Y. What that means is, like, for each class, you will predict what the prediction is going to be, what predicted label is going to be for that feature. Whereas the weight matrix is constant. This one is kind of confusing. I'll state why as we go down. So here we are going to identify a feature vector that gives the best Y or the hypothesized y. That's what he says. And here he says this is called an output space. There are certain cases where just having a simple classifier doesn't work. So I think that's why these two techniques we are going to cover. And these were some of my notes. Like I use ChatGPT to pull up or clarify things that I don't understand. So he talked about like W is indexed by Y. So that's what he says here. W is indexed by Y, which means that there is a weight vector W associated with each class label of Y. So like for each one of these class labels, there would be a separate weight vector. That's the reason why it's saying W is indexed by Y. So in case of multi-class classification, this means that each possible class of Y, there is a corresponding weight vector. So if you have multiple classes, then you might have different weights, as I explained. Each one is responsible for distinguishing one class from the others. These weights are used to predict probability or the score for each class during classification. In summary, W indexed by Y means that there is different distinct vector for each class in a multi-class setting.
Rufin, what question did you ask ChatGPT to get this response?
I usually, I just asked like, what does it mean? I give this formula, and I asked like, what does
But
this?
how do you give this formula to ChatGPT? It's an image, right? Or do you
Yeah,
type
you
it
can
out?
give image. You can give image.
Ah, okay. Nice.
So I use it like I'm kind of a super user. And
Hey,
it, yeah, go ahead.
sorry, Rupi, is this notes completely based on the professor's video, or did you refer to any other material as well?
No, I refer to Chat GPT and professor's notes. So these like this is professor's notes. These are my own notes.
I see. Okay. Yeah,
So
because what I was observing is just going through the professor videos, it may not give like
yeah,
full length of what we need.
yeah.
Especially just from my perspective, I don't have much background on artificial intelligence. I haven't worked on it, but even math also I'm trying to catch up. It's been very long time after my bachelor's. So I'm not sure. I'm just curious how others are coping up with the math as well, algebra and calculus. Did you guys go over any prerequisite tutorials to brush up our math skills, etc.? I'm looking forward for some suggestions as well.
Yeah, I think we can cover. Let's go through the lectures. I think I have done some like prereqs. I think on Coursera there is mathematics for ML. So there are
I
like a
see.
course series. So you could go through it. I think I haven't gone through all three of them. I finished the last one. I finished about 80%, and then the coursework started. But
Oh my God, Rufi, you're exactly where I am.
yeah,
I did the exact same thing.
yeah. And what I have noticed,
Nice.
you feel like the concept, but you forget unless you have to go back and go back and like refresh. So you have to just drink from the fire hose and like use Chat GPT or these tools to help build that knowledge. You have to go through the lectures, but you have to supplement through some readings or through Chat GPT to help
Okay.
explain the concepts. So that's
Thank you.
how at least I am dealing with it. So
A
structured class.
question.
Yeah, go ahead.
I'm so, yeah, a question that I had was I saw that there were a lot of readings attached to every video. Is that right? So do you guys usually go through the documents that are being attached, or is that something that you guys usually look for after you're done with all the videos?
It just depends on how much time I have that week. Uh,
Makes
I
sense.
haven't,
Yeah.
I haven't had a chance to go through. I think, frankly speaking, I want to go through them, but I don't have time. I think my criteria is to finish the videos and try to understand the material as much as I can,
hmm
and jump onto the assignments. And then I think, if time permits, then I will look into
Yeah.
the readings.
Yeah, the reason I'm asking this is because when I started week one module, I mean, like everybody here, right? It's been a while since I mean, was academically, reading and whatnot. And I got into the textbook material in week one module, and I got stuck there for a good 1 week. And then I had to like stop it midway and then jump to the videos and then assignment one. So just wanted to get an understanding of how do, people get it. But I think let's finish the module and then we can discuss that later too. That works for me.
Yeah. I think it's just, if you have time, you could read it, but yeah.
Okay. Thanks
We
for feeding.
can, yeah, I think maybe we can divide and conquer. If someone doesn't understand, share your notes. I think we can like teach one another. I think that's the best way to maximize the learning.
I agree.
Yeah.
Yeah.
Structured classification. So I think somebody asked what is structured classification. I think the lecture doesn't cover what it is, but I think I just did some like chat GPT, and it said like it's examples such as named entity recognition. So here is the example. You're trying to classify like entity recognition. Barack Obama is a person, Hawaii is a location. That's named entity recognition. Another example is sequence labeling or part of speech labeling. So you just label each word with the grammar, like the part of speech. So the is like determinant, cat is a noun, and verb. So that's that. So it's used when I think like structure classification is used when your output is more than just single label. It could be a sequence, tree, or a structured object. So that's structured classification. So your output is not just a single label like simple multi-class classification. It's a tree or a sequence. So different features approach applies to these tasks by extracting or modifying features based on specific label you're hypothesizing, and thus creating a more complex relationship between inputs and outputs. Here is one example when labeling whether a sentence belongs to health, sports category. The features you consider may change depending on the category. As shown below in the image, it says if the label being hypothesized is health, then certain words may become more important. Example, doctor or medicine. If the label being hypothesized is sports, different words may be relevant, like team and match. So that's what hypothesized mean. So if you're predicting health, you will have a different weight vector or a feature vector, different feature vector, which identifies relevant words based on that hypothesized label. So
Is there a reason that the different features performs better than the different weights? Do we know for the structured classification?
structure classification is like when you're using structure classification, at that time you're using the different features technique.
Mhm. And because I was just thinking, well, I might be wrong, but I was thinking that the different features and the different weights technique might be isomorphic in some way, but I'm not sure. Like I don't know either, but
Yeah, I think
Yeah, I agree. I think he says that.
so each technique is used for a different purpose. So he says is different weights is used for neural nets and different features is used for structured classification.
I I guess I didn't have it that concretely. I think I had it more like different weights lends itself more naturally to neural networks, because right the feature can be passed into a neural net. But
yeah.
I think that the two techniques are pretty much isomorphic with each other.
Yeah.
Could you scroll up back to the the equations again? So I just want to make sure I understand this correctly. So the different features is basically taking a one-dimensional weight vector, and we basically have 10 feature vectors if we have, say, n equals 10, like 10 categories. And we're basically doing, I guess how
This is the
I'm thinking of it
example.
is we have like 10
There
neural
is an
networks,
example
right?
he covers. I think it will become clear as we go down. So this is just an overview. He'll go deep down in subsequent
Okay.
slides. So will cover that. So hold on. So the application is like topic classification. So he is covering an example using different weights as well as different features. So here you can understand that like the input document or the input sentences like too many drug trials, too few patients, and the health label could be the output spaces, health, sports, or science. So if you go by bag of unigrams, we are going to only look at drug, patient, and baseball. So that's going to determine your feature vector. So f of x with that sentence becomes 1, 1, 0 because we have one for the drug and one for the patient. And like here, different weights, we are assuming these weights. So he just assumed these weights. So 5.6 and -3. So the highest dot product becomes 7.6, which is like 2 times 1 and 5 times 6. So addition of that is 7.6. That's the highest dot product. So the topic is health. So like you look at the sports, so you assume again some weight vector, 1.2 minus 3.1, 5.7, and your like the sports is like minus 1.9. And he didn't calculate like science weight vector. He just gave this example, and he's saying that you're picking the erg max. Like here, if you see, it's the erg max of those 3 weights, and the max between these 3 weights is 7.6. So your prediction is going to be, your prediction of y is going to be health. So that's that. So different features. Any questions on this? Okay. So different features. So you have different like feature vectors. So they are replicated for each class. So fx, like for health, there is going to be a separate feature vector. So in this case, you have 1, 1, 0, 0, 0, 0, 0, because like that's health, and health is based on drug and patient. And for sports, 1, 1, 0, because sports drug could be relevant and patients could also be relevant. That's what he says. And so those were 2 features. So he also says that these are called as conjective features that I explained in the previous slide. So it looks at both X and Y. Features in DF are indicators. Like it's a sentence containing word I, like for Y is equal to sports. So that's like an indicator. And then
So Ruby, how did he? So f of x, assuming given y is held, and 1, 1, 0, he just picked it up and said, "This is." I guess I missed this part.
yeah, I think
1, 1, 0 in red. What's that about?
1, 1, 0. I think that's like drug and patient. Like you can say
Oh, the same. Okay.
it's same. For sports also, he picked up, I think, drug and patient. It could
Wait,
also
so
be a sports topic.
right. I thought the reason we get the 1, 1, 0 is just the bag of unigrams encoding from the beginning, right? And so now we just like switch its indices depending on the category.
Oh, yeah. Okay, gotcha. Health,
And
sports, science.
it's also dependent on the sentence that was given in the beginning, right? So yeah.
The confusing thing is like, why would drug and patient result into sports? So I think what is the distinction that's not clear? Because drug could be relevant, but patient may not be relevant. So I don't know why why patient is relevant for sports level.
So our feature space is 1, 1, 0, right? That's
Yeah.
our feature space.
Yeah.
So what he's saying is, the feature space given the outcome is health, right? So if the outcome is health, then there are And this is basically one vector per outcome, right? One vector per predicted outcome, correct?
Per feature.
Per feature.
So, oh, sorry. It's a feature. It's a different feature, right? It's a different feature per output label.
Yeah, so output label is the outcome, right?
Yes. Hypothesized outcome.
Yeah, and in this one, he's hypothesizing that
It's
this
health.
is health, so the first one is 110.
Yeah.
And the second one, the hypothesis is sports, so that's the one they've chosen.
Yeah.
Okay. I think it makes sense.
And
The
then,
assumption is that if y is equal to the third label, then it would just shift to the third part of the feature. That's
Yep.
what we would think. Yep.
And then he'll probably calculate the dot product and see which one is highest.
Mhm.
Right?
yeah, he said like this, it's pretty peculiar. It's very confusing. This different features vector. He mentions it when in the lecture, because if you see the weight metric, he says it's constant, but you're taking the, like in here, we had a weight matrix for health, sports, as well as for science, but you're just creating a single vector and you're stuffing all these weights into the single vector. So you have like a long health feature as well as sports feature, and you also have a long single weight feature. And these weights are, if you can see, it's like these map to the health. So these are the weights which are concatenated into a single vector.
So one thing I'm kind of confused about is that, so I understand this is doing like flattening this into one dimension for the weight vector, but
Mhm.
isn't this the same as if you just made a 3x3 matrix and then multiplied by the same 110 vector for the different weights?
Oh yeah, I think you could do that, but yeah, but I didn't get into the math. Yeah.
Yeah, that's why I was thinking they were isomorphic because it seems like the same thing, but I'm not sure if I understand it fully.
Yeah. Maybe a good question. Maybe somebody can take a note and clarify, and maybe let's come back to it. So
Daniel, isomorphic was a big word.
Sorry, what?
yeah,
Isomorphic was a really big word.
even I didn't
You
understand what
mean,
by
oh,
isomorph.
sorry, it's a math term. I have a math background, but it basically means that the behavior of one abstract object is the same as the behavior as another abstract object.
Okay.
So all I'm trying to say is that the answer when you train using different weights versus different features should be the same, at
Oh,
least if I'm understanding correctly.
gotcha.
But the examples he gave is different, right? He says that different weights is used for different purpose and different features is used for structure classification. So from the example, it doesn't seem that they're isomorphic.
We can double check lecture offline, but I'm pretty sure he said these are kind of variants of just doing the same thing. It's just that some are easier for some use cases than for others.
Okay. Yeah, I think we can. I think I was just thinking sometimes if we get any questions, it would be good to attend some office hours or post that question onto the like the ed discussion board and get it clarified.
Mhm.
So Daniel, like post a question on ed and let's see what someone like TAs may answer back. But
Okay, good idea. Thank you.
so here he's dry running through one example. He goes through like different weights vector. He doesn't go and explain different features, but I think I took some notes. So here is the for loop. You go through the epochs. You are calculating the erg max, different weights for a given prediction, which is like So you're calculating the prediction based on 3 vectors that you will calculate and pick the max one from there. And if your prediction is not same as your true label, that's when you do the update. So the way you do the update is you reduce the score. That's why there is a negative here for the prediction, and increase the score for the true class. So that's why there is a plus over here. So you're adjusting weights, the predictive weights and the true weights. So that's what he explains, and he runs it through one example. For that previous example, too many drug trials, too few patients. That's the feature vector. The true label is health. And the second example is 101, which is baseball players taking drugs. And the true label is sports. He says assume default prediction is y is equal to 3. So you start with just some random weight vector, which happens to be 0, 0, 0. So these are 3 separate vectors. It's not a single vector, but these are 3 separate vectors. So wy1, wy2, and wy3. Then we update on this first example, which is 110, and you try to calculate your y prediction. The y prediction was 3 as here, like that's the default. And y, the true label is 1 from here. Your learning rate is 1. So then you update your y prediction is 3, which is incorrect. That's why you will subtract this weight. Like, I think, no. So the prediction is health. So y is equal to 1. So this is for y. So this is for y1. So this is correct. So you will add. Your prediction is 3. Your true label is 1. So your prediction is not equal to your true label. That's why you need to update both of these terms. So the first term being this one. So you add the features and you get this. And you subtract because your prediction was wrong, because which was 3. So you go to that vector and you update, you subtract the feature vector. That's how you get -1, -1. So once we have that, so that's the updated vector. Then you go to the next sentence, next example. Your prediction on the next example is, he calculates 1. I think this is a calculation. I do have an explanation how that happens to be 1. So what you do is you have 101. That's your example. That's your feature vector. And here there are 3 weight vectors, 110, 000, -1, -10. So you calculate your 3 dot vectors. So for here, W1, which is 110 multiplied by your feature, would give you 1. And for the second one, it's 0. And for W3, it's going to be -1, -1 multiplied by the feature vector. It's going to be -1. So the max of this is 1. So that's why, where is that? So this matches with this. That's the explanation why pred is equal to 1.
Question. So do we have a single weight vector and then different feature vector? So what we're showing here as 3 weight vectors is actually one single array that we have. Is that right?
Single. No, this is 3 separate. Just for
3 separate. Okay.
That's 3 separate weight vectors.
Got it. Okay, so then it's essentially DW then. So it's different vectors and a constant feature.
Yes.
Okay, got it.
So once we have this, like we calculated y prediction for the second example, and the true label is 2. So the prediction is again incorrect. So you will update. One is where one is here. So you penalize that weight by subtracting -101, and you get that. And you will boost this second vector because that's the true label. So
Mhm.
+101. So that's the updated weight vector. And
Makes
you
sense.
do a change in W3, and then you bring it down here. And I had this.
W3 didn't change though, right?
No, yeah, you only update two of them. You penalize the one which is incorrect, and you boost the true label. So these,
Okay. So why not the third one?
because here, if you see, that's like, because that's not changed. Like with the prediction, there's no relationship with the third one. That's why you just carry.
Because we're not predicting scientists.
Yeah.
Okay.
So here I was confused. Like why pred, why do you subtract this versus why do you add? And the intuition here is, imagine weight vector WR like votes for each class. When the model makes mistakes, we need to take away the votes from the wrong class and give more weights to the correct class. So that's the explanation.
So you're trying
Yeah.
to adjust it and balance it out.
Yeah.
Yeah, I think it's the same, or you can view it the same as with binary classification, where when it's correct, you add, and when it's wrong, you subtract. Oh, sorry. When it's correct, you don't do anything. But yeah.
So that covers that. And then he gets into multi-class, which was like very confusing for me. Even till now, I had like, I think I understand it. He talks about you calculate the probability, like this is the predictable, the class actively computing the probability for. So you need to compute the probabilities for each prediction. And then, so that's calculated by this formula. And you add up all those three probabilities, and they need to sum to 1. And he says this is, did I miss something? So this is equivalent to binary linear classification. So like that was just one explanation that he had, but this is multi-class linear regression. So here what you do is you calculate the three probabilities, and you calculate the gradient, which is this gradient for the loss. And that gradient or the derivative of this function is this. So it's the gradient plus sum of all possible output values. So if this is the y I is equal to 1, which is true, in that case, there is no gradient update, he says.
So I think this is the same thing from last week, where it's the probability can approach 1, right? And like as the probability approaches 1, like our gradient